Let's talk about tactics. In the last chapter, we didn't talk much about proving things. There are some exercises that you can do, but it's really kind of just the same as proving things about lists of numbers and numbers themselves and so on. So we've introduced complexity. We've introduced flexibility in the way that we can write things down. We've introduced ability to make definitions much shorter and more reusable. But the way we reason about them hasn't changed. The next chapter, we're not going to introduce any new programming facilities, but we are going to introduce a whole bunch of new ways of reasoning that are useful. Okay, first useful thing. So what are the reasoning principles we've seen so far? We've seen rewrite, we've seen reflexivity, and we've seen induction, and we've seen destruct, which is kind of a degenerate case of induction. The next one is apply. Apply says, if we've already established some theorem, and the thing that we're trying to prove now matches the theorem that we already proved, then we're done. So for instance, suppose we're trying to show, for some reason, that if we know n is equal to m, and we know that the list NO is equal to the list NP, then we know that NO is equal to MP. All right, why does that make sense? It's kind of a silly theorem, but it makes sense because we know two things, and if we substitute one equality in the other, then sorry, I'm standing too close to read. Okay, so we can do this by rewriting, but we can also do it just by apply. And let me now go over here and get to the tactics file. There we go. Okay. Okay, so if we do a rewrite, then we see that the goal is exactly the same as one of the hypotheses, EQ2. And now we could, of course, finish in the way that we have before. We could do one more rewrite, and then we'd have something with the same thing on both sides, and then we could say reflexivity. Or we can just finish in one step by saying apply EQ2. So apply says take something that you already know that matches the goal and use it. Apply is more interesting when we use it with conditional hypotheses. So here, EQ2 is not just an equality, it's an equality subject to some hypothesis, so it's an implication. And it says, for any Q and R, if Q and R are equal, then Q followed by the list QO is equal to the list RP. Once again, don't try to figure out what this means mathematically, it's just a silly example. The reason I want it as an example is to show you that if I apply EQ2 to the current goal state, it's going to have to do some matching, some pattern matching, some unification, strictly speaking, to lay the conclusion of EQ2 on top of the goal and see that they match. Right? Because the goal has an N and an M in it, and EQ2 has a Q and an R in it. But Q and R are universally quantified in EQ2. EQ2 works for any Q and R. So I can apply EQ2, and it solves that unification problem. Because EQ2 was a conditional hypothesis, it leaves me with a subgoal. So previously when I said apply, it just finished the proof. Here, because EQ2 has a hypothesis, there's something that, once we apply it, there's something left to prove, and that takes one more step, which is, in this case, just a use of EQ1. Okay?
How does apply no to work on that proposition, the one in the conclusion of?
So how does apply no to work?
Sorry, never mind. I was looking at something wrong.
Okay, right.
Yeah, can I? So when you do apply EQ2, does that looks at the first part of your conditional? EQ2 is a conditional for all Q and R. If Q equals R, then, or Q equals R implies. So it looks at Q equals R, and it matches that to N equals M.
No. So it does exactly the opposite of what you're saying. So the question was, how does the pattern matching work when it's trying to unify EQ2 with the goal state? Let's go back and look. Sorry. Ugh. There we are. Okay, so when we say apply EQ2, it looks at the conclusion of EQ2. Looks at the conclusion of EQ2 because it's reasoning backwards. So we're trying to show the thing in the goal, and we know EQ2. So the reasoning that you're doing with apply is you're saying we can prove something of the form of the goal, assuming Q equals R. So Q equals R is going to become the subgoal. And in order to do that operation, we need to lay the conclusion of EQ2 over the top of the goal state. And then it's the unification process that fills in the appropriate values for Q and R, namely N and M,
Right.
allowing us to go forward the last step.
But this strategy is like a implication introduction. I've got to should go from the antecedent to the consequent. It starts with the consequent and says go back.
It starts with the pattern matching. When you use an apply against the goal state, you're always matching against the conclusion of the thing that you're applying.
What if you just apply
Okay. So could we somehow, instead of working on the goal, could we somehow mash EQ1 and EQ2 together? Yes. And let's see, that might even be next. So hold that question for a minute. No, it's not quite next, but I'll come back to answer that question in a couple of slides. Okay, so all right, let me just show you this bit. Okay, here we are. We're trying to show this slightly silly thing. It says, if the list AB equals the list CD, and the list CD equals the list EF, then the list AB equals the list EF. And we've already, I skipped over doing it, but just above, we have taken the trouble to prove already that equality is transitive. So for any NMO, if n equals m and m equals o, then n equals o. So it seems like we ought to be able to apply trans EQ to solve this goal. And indeed, we can make a little progress. So we can apply trans EQ. Sorry, let me just show you. Apply trans EQ. Oops. Yes, excuse me. So simply trying to apply trans EQ doesn't work. Why doesn't it work? Well, what is the message? You probably can't read it. It's very small. It says, unable to find an instance for the variable m. So what happened?
Try to unify.
So we tried to unify. So the goal state looked like something equals something. And we tried to unify that with n equals O. Well, n should have been the list AB and O should be the list EF, so what's the problem? That should unify. Here's the problem. So as far as just laying one on top of the other, it did unify. And that caused us to realize that the variable, what is it, n must be the list AB, and O must be the list EF. But what about m? It can be anything. As far as the unification algorithm is concerned, m could be anything. And that will make apply unhappy. In a chapter or two, we'll see a more general version of apply that would not get unhappy in this situation, and that's often useful. But apply is picky about this. It says not only the goal state must match must unify with the conclusion of the thing that you're trying to apply, but also all of the unification variables that are introduced in that process, namely in this case x, n, m, and o, must be determined, must be resolved by that unification. And in this case, m was not. So,
but if transik had a universal quantifier in the statement, it would be happier.
Transeq does have a universal quantifier in the statement.
Over n.
Transeq, if we printed the type of transeq, it would be for all x, for all NMO. So transeq is a completely generic theorem. It works for any NMNO of any type x.
But if we don't do intros like m here in our example,
so if we don't do intros m,
like not the same way as m, like I think E or M.
so like are you saying if we just left out doing the intros of, well, but we need, well, it wouldn't work anyway because we have to intros the same number of things as there are quantifiers that were at the beginning of the goal. But I see your intuition, but it wouldn't work anyway because C and D are mentioned other places around, so we have to have names for them.
Like in this particular example.
Yeah. Okay, so let me tell you what does work in this example, which is to tell the apply tactic, here is the value that you need to use for m. And we do that by adding a with clause, like this. So it says apply trans EQ, and when you need a value for m, here it is. Okay, and that then makes it easy. Okay, next tactic, please.
So, apply is a tactic. With is a tactic transformer?
No, apply is a tactic and apply with is a tactic, is the way to think about it. Or with is an optional argument to apply.
Are these are not primitives to coq. We're just learning different tactics that are in the prelude of the coq.
apply with is built into coq fairly deeply. Let's see. Yeah, the way to think about it is apply is a primitive thing, and apply with is a variant of apply. So it's another built-in tactic that takes some extra information and uses it in the process of doing the apply. Please.
Can you use the apply with that existential quantifier?
Can you use the apply with tactic with existential quantifiers? No, for existential quantifiers you need something else, and we'll get to that this afternoon. All right. Oh, more questions? Yes.
So instead of intruding the two equality conditionals, conditions, you can keep them down and just apply transec.
Yeah, you probably could just apply transec if you left off the last two variables in the intros. Let's just try it. I think that will work. So if we left off those, then because then, so why is that? Your intuition was correct, but just to spell it out for people. So transec takes 3 arguments NMO, and then it gives you a big conditional thing. So here the goal state matches the whole big conditional thing, not just the conclusion of that condition. So now the unification has more to work with, and we get all of the variables instantiated. Okay, more questions. Inversion is the next tactic on our list. So when we give inductive definitions of data types, those definitions have some crucial properties. For example, for NAT, the constructors S and O are disjoint in the sense that the subset of natural numbers whose top constructor is O is disjoint from the set of natural numbers whose top constructor is S. And that's just obvious thinking of them as trees. But it's a crucial reasoning principle. So, and hence, a natural number that begins with O is never equal to a natural number that begins with S. And that's true of any inductively defined type. The constructors are always disjoint. Moreover, the constructors are always injective. That is, if I have an equality that says successor of X equals successor of Y, then I immediately know that X equals Y. It's not true for all functions. So certainly if X minus 1 equals Y minus 1, it does not follow that X equals Y, because that would be true of 0 and 1, which are not equal. So it's a special thing that's true of constructors. And the inversion tactic allows us to invoke these principles of injectivity and disjointness together. Now, something to know about coq is that because it's been under development for a long time and lots of people have done things to it, in general, there are probably 6 ways to do any given thing in coq. So you might wonder at this point, well, there are 2 different principles involved here. There's the principle of injectivity and the principle of disjointness. Are there tactics that invoke each one of them separately instead of mashing them together as inversion does? And the answer is yes. And some people